the exam is still this Thursday, correct?
We're gonna have the exam after the quiz, otherwise the quiz makes no sense.
Okay.
So. I haven't been running the schedule yet, but, we need to finish this, and we need to do the quizzes first. So chances are it's gonna be next Thursday next week. What I tend to do with the quizzes is once everybody has taken it, I will post the answers in D12. For me, it's a learning exercise. You review the questions, you see the answer, and go for the exam. So Wednesday morning is gonna be the last time that I allow somebody to take it. If you are taking it in the testing center, which I hope is not happening, but if you are, your absolute deadline to take that is Wednesday at 10:30 a.m. when everybody else has a deadline to take it. After that, you cannot take it any longer. I will post the answers in D12, and you lost the chance to take the quiz. Okay, which of course is extra. Alright. So this Thursday, Tuesday next week, and Wednesday. I mean, if you guys are ready to take it tomorrow, I could do it tomorrow. I did not want to show up and be the only person there because nobody else shows up. I should have gotten my second year and start this Monday, Tuesday, but it didn't happen, so this is the way it's going. So yes, the second exam is then gonna be not this week, but next week, Thursday. I mean, the first exam. All right, so continuing where we left off on a concept. The concept, of course, is a cyclic form of ether, but any ether is effectively a oxygen with alkyl carbons of either side. We looked at ways of making ethers. We looked at the Williamson ether synthesis. You had an alcohol, you put them with a strong base, maybe an oxide ion, and then that oxide ion attacked an alkyl halide in an SN2 reaction. We looked, well, we're gonna remember that. So, yeah, let's look at this. So, your Williamson ether synthesis you have some sort of an alcohol, you put a strong base, and that strong base, something like sodium hydride, sodium, whatever, attacks, forms your alkoxide ion, strong nucleophile, which can then go ahead and attack whatever, let's say, this alkyl halide, SN2 reaction, and that would give you an ether. And this is can be an unsymmetrical ether. We don't need to have, the same groups on this side because they're coming from two different molecules. Yeah.
It doesn't matter if it's ethanol too, or if the methanol works just fine. Or are you selecting on what nucleophile it is?
Whatever alcohol you have, that's the alcohol that's going to form your compound.
But could it be ethanol?
It could be anything at all. That's the whole point, that you can put different groups in here. So, this is an SN2 reaction, which means this works best on a methyl or primary halide. So when you're planning your synthesis, you try to have, let's say this was a benzene ring. Well, you cannot put the benzene ring here and have an SN2 reaction. The benzene ring is going to need to come from this end and this, and the alkyl halide be the least substituted one and certainly not an aromatic one. Okay, so you kind of plan your synthesis that Then was alkoxy operation. Demercuration. So in chapter 8, when you had an alkene and you wanted a markovnik of alcohol, you had a couple of options, but one of them was an alkoxy mercuration, demercuration. You would have mercuric acetate, which would make a mercurium ion, and then you would put some water, which would attack and open this from here, the most substituted carbon with the most positive charge. And then you needed to get rid of the mercury, so replace it with a hydrogen, and that would give you markovnik of alcohol, right? Now, if this solvent were an alcohol rather than water, then at the end of the day, you end up with this piece rather than an OH. So that, of course, would be now a ether. So if you're doing an oxymercuration, demercuration, using an alcohol as your solvent and as your nucleophile, then that is another way of making ethers. All right, and dehydration of alcohols, remember we looked at if you have an alcohol and you put it with sulfuric acid and you heat it and whatever. So there's two things that can happen. One is an elimination, right? You pick up a hydrogen, it leaves, goes across cation, eliminate. The other one is another molecule of solvent will come in. This becomes a good leaving group. This attacks, this leaves, and then eventually you will lose this and you form an ether. Okay, so whether it's an elimination or a substitution, this is one way. Now here you're going to make symmetrical ether because it's the same molecule attacking itself. So on either side, you're going to have the same group. But one of the products that you can form will then be this symmetrical ether. Okay, as part of the general dehydration of alcohol, you can also have substitution reactions. So those are different ways of making ethers. And you have it here, the Williamson ether syntheses, and blah, 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 blah. Let's look at problem 2 before we go very far. So this would involve Williamson ether synthesis, right? So this one is looking at this alkoxide ion attacking this methyl iodide, SN2 reaction, and the product would be this. Now, the more important question would be, if I give you this, and I ask you which are the best starting materials, you have two possibilities. One, to have this attacking this. The other one would be to have this attacking this to give you the same product. Which of the two is your best option?
So that's one on the right, one on the right.
So what we're attacking is this.
Yeah.
This is a tertiary alkyl halide. SN2 reactions do not occur with tertiary alkyl halides because those large groups are blocking the backside attack of your nucleophile. Right? So this would be impossible to occur, while in here my alkoxide ion is attacking a methyl halide, 3 small hydrogens is a lot easier for this to occur. Okay, so this would not be an option. But on paper, you know, either one theoretically works, but the reality is that only one of them works. So in here, your answer would be there's no reaction because this is a tertiary halide.
What if it's a secondary?
Secondaries work not as well as methyloprimary. So if at all possible, you would prefer a methyloprimary. If your choice on either side is, you know, one is a secondary, one is a primary, make the alkyl halide the primary that the alkoxide ion is attacking.
But this is because we have the nucleophile present in them.
Well, both of them you have an alkoxide ion as a nucleophile.
Yeah, but this is we're assuming it's like an SN2 reaction.
It is
SN.
an SN2 reaction, you're not assuming that it is. Yeah, it's a strong nucleophile and therefore that involves an SN2 reaction. Okay, so this one is telling you, okay, you have ethyl phenol ether, and I want to make this first using a Williamson ether synthesis, and second doing an alkoxymercuration demercuration reaction. So show me the starting materials, all the reagents that will form this, first using a Williamson ether synthesis, and second an alkoxymercuration demercuration. So for your Williamson Peters synthesis, which bond are you gonna make? Blue or red?
The red.
Are you gonna have this alkoxide ion attacking this halide? Or are you gonna have this alkoxide ion attacking this halide?
The second one.
The second one, this is a primary halide. This is an arrow halide. You cannot possibly have an SN2 reaction under these conditions. Okay. So this is really your only option. You're gonna, let's say, start with phenol. First, you're gonna put a strong base, let's say some sodium hydride. And second, you're gonna add your alkyl halide. Right? The hydride will form the alkoxide ions. Then you add the halide, SN2 reaction. And you form this. Okay. So an alkoxymethylation demethylation involves starting with an alkene, right? To an alkene, you add the mercury, form the mercurium ion and then open with, in this case, an alcohol. What's gonna be my alkene here? And what's gonna be my alcohol?
Alkane would be the phenol.
You're not gonna get double bonds, these are here at the end. When you're doing this reaction, the double bond is no longer there at the end. Forget about the fact that the double bonds in benzene are not gonna budge for a reaction like this, but you're no longer there. So your product is not showing the double bond anymore. But where was the double bond initially? That's right, right here. Okay. So what you're gonna do is you're gonna start with ethene. And you're gonna do your alkoxy operation, this operation, which is you're gonna put mercuric acetate. Your solvent is gonna be phenol. And then you're gonna add this, you're gonna have the mercury there, and we need to exchange the mercury for hydrogen, which is coming from sodium borohydride, and that will get you your final product. This piece is coming from here. And this is coming from here.
So only when you're trying to get an ether product is when you use the alcohol, correct? In the oxymercuration.
When you're trying to get an ether, yes, you use an alcohol. Otherwise, if you solvent here with water, then you would have formed the alcohol. You might call it alcohol. You have water here. Well, you can't really have any, there's no more carbon chloride. comments here, but that would be what you would say. Okay? So, this is a minor thing, but sometimes different alcohols react differently. This alcohol here is a primary alcohol. All the others in the sugar are secondary alcohols. Primary alcohols more exposed, this is kind of has a CH2 and the OH, these are attached to this ring, they're a lot less available for reaction. So this OH here is a lot more reactive, and you can get it to react pretty much exclusively. In this case, your base is sodium oxide, silver oxide. We'll get to talk about silver salts and silver oxide and how it is used as a base. But this is the base, there's an oxide ion, and then this would be a Williamson ether synthesis. Minor detail, don't worry about it. You are not using something like sodium hydride because that is so strong that it would start removing these hydrogens as well. You need something that is fairly bulky, like silver oxide, so that because it's so large, it can only reach something that is really exposed and not the ones that are directly attached to the ring. So that's why we're using this base. But that's a minor detail. Now, when you're using phenol, the pKa of this thing is about 10, as opposed to a pKa of 17, 18 for your average alcohol. That means that, this is a lot more acidic because, of course, the conjugate base is resonance stabilized, so it's a lot more stable conjugate base, which makes it a stronger acid. So you don't need a stronger base. You don't need sodium hydride. Sodium hydroxide is plenty strong in this case to form the alkoxide ion. But if this were any other alcohol, methanol, ethanol, whatever, you need the strong acid. And we talked about an alkoxy mercuration demercuration, which gives you, of course, your Markovnikov product, except that rather than having an OH, we will have an OCH3 or whatever the alcohol happens to be. So let's look at problem 3. Oh, we did problem 3. We talked about when you have alcohols, you can, the word here is condensation. Now, we've talked about condensations before in an esterification reaction, right? We talked about condensing a carboxylic acid with an alcohol, right, effectively losing hydrogen and OH, and then connecting this piece with this piece coming from the alcohol. And of course, in the process losing water. This is typically done under acidic conditions. The forward reaction, where you get two organic molecules and condense them into one organic molecule. Organic is something that has carbons and hydrogen. So that is condensing two organic molecules into one and losing water in the process. This is a reversible reaction. In the forward direction, this is your condensation. In the reverse, I'm adding water to an ester under acidic conditions to form the carboxylic acid and the alcohol, right? In the reverse direction, this is an acid hydrolysis, right? Adding water under acidic conditions. So, in biochemistry, condensation reactions are tremendously important because this, and acid hydrolysis, because these are ways of putting together large biomolecules. So for example, if you condense a fatty acid with an alcohol like glycerol, then you form triglycerides that way. Or if you eat a triglyceride, you can hydrolyze it, metabolize it, break it down as you digest into your fatty acids and the glycerol and whatever. So that is one type of condensation reaction. Then of course, your fats, oils, that type of thing are esters. Now, you could have two alcohols. And technically you could do the same. Use hydrogen and OH, and now connect these two pieces together. In the forward direction, this would be a condensation. In the reverse direction, this would be an acid hydrolysis. This is again occurring with acid, and you would have an ether and water. Important ether molecules occur, or ethers. So molecules that have lots of OHs are sugars. And you can condense sugars together, and the way that they condense together is by forming these ether linkages between your sugars, right? What we call glycosidic bonds. So sugars, disaccharides, trisaccharides, polysaccharides, formed by joining sugars together, your monosaccharides, and forming these ether linkages. Okay. And of course, you can break it apart by hydrolyzing. Now, the third type of condensation reaction that we're going to look at is having a carboxylic acid. This is going to be later. But a carboxylic acid condensing not with an alcohol, but with a nitrogen equivalent of an alcohol, what we call an amine. And you would have the same thing, except now what you're forming is an amide, and of course you use water. And of course you can hydrolyze this. Amide bonds are what we call peptide bonds. You condense the carboxylic acid in one amino acid with the amino group in the next amino acid and form these amide bonds, right? So,
Is that a hydrogen bond to a nitrogen in the product?
Yeah.
I'm sorry, is that a what? Oh, a hydrogen. And your nitrogen needs to have 3 single covalent bonds. And the amino acids are joined by amide. ethers, esters. This, if you are referring to sugars, this would be called a glycosidic bond. If you're referring to amino acids, this would be called a peptide bond. But regardless, that's, that's important. But condensation and hydrolysis are very, very critical reactions. In organic chemistry, that's how we make a whole bunch of different functional groups. And of course in biochemistry, where rather than putting massive amounts of acid, we have nice enzymes that are a lot more sensitive and can do these reactions. But those are basically the reactions that we do. Okay. So right now we are interested in putting ether linkages together. So there's two alcohols. We use water, connect this to this, that would give me an ether. This is not an easy reaction, a lot easier if you have enzymes in your body, but in the lab, this would require very strong acid, very high temperatures. It's not something we typically do. There's nicer ways of making ethers than this. This is kind of brutal, not to mention you're also going to have elimination, which is an issue. Okay. But there's that. All right, so those were the three ways of making ethers. And their review, we saw all of them before. Reactions of ethers. So if you put an ether in the presence of an acid, well, we know that this oxygen is going to pick up hydrogen. Now this becomes a good leaving group, right? We looked at this type of reaction where we had alcohols to make it a good leaving group, but of course the same is true with ethers. You put it in the presence of acid, and now this becomes a good lead. And so a nucleophile can come in and attack, and your good leaving group leaves, right? So depending on what you're trying to make is what the nucleophile is going to be. If your nucleophile is a bromide ion because you put this in the presence of HBr, then your product is going to be an alkyl halide. And of course, an alcohol on the other end. Okay. So we're effectively cleaving. This is the reverse of what reaction? When you put an alcohol or the alkoxide ion with an alkyl halide to form an ether. That was a Williamson ether synthesis, right? We came in with a base, formed the alkoxide ion, this attacked, and gave me the ether. Well, now we're doing the reverse. Put the ether in the presence of HBr, and you form the alkyl halide and the alcohol. Okay. So let's look at problem 4. So we have ethyl isopropyl ether reacting with HI, hydroiodic acid. Show me the two products of it. The two most likely products. Because remember, this is an SN2 reaction. let's write a mechanism for this. So what happens first?
The oxygen attacks the hydrogen.
The oxygen attacks your acidic hydrogen, right? I mean, this is a really strong acid. This is probably ionized already, but let's write it like that. This attacks this, and this opens up. So your intermediate, I'm not asking you for that, but I'm writing the mechanism. And so now we have this better living. Now, my iodide ion that forms in here could attack this carbon and have this leave, or it could attack this carbon and have this piece leave. Which is more likely to occur, red or blue?
Blue.
Why?
Because it's all primary.
Correct. Red, because this carbon is primary, while this carbon is secondary. In an SN2 reaction, attack on a primary carbon is going to happen a lot faster. So it's not that this is impossible, but you will likely get a lot more of attack here and form ethyl iodide and this alcohol isopropyl. Now, one of the issues that you need to consider here is that you now have an alcohol, and your alcohol can react with HI as well, right? So this would then go ahead, attack HI, form this, and now your iodide doesn't have a choice. There isn't a much better option, so it can attack like that, and now you would have some of this and water. So that is potentially happening as well. But hopefully, you know, with a limited amount of HI and whatever, you should expect mostly to get these two products. But certainly, it wouldn't be surprising to also be getting some of this. Okay. Okie doke. So again, you put this with hydrogen. Now, in here, your bromide ion really only has one option. What's that option? The primary carbon, right? It's not gonna go for an sp2 carbon. There's no possible SN2 reaction happening here. This is gonna go for this and form the alcohol, phenol, and ethyl bromide. You cannot, this is not an option at all. You don't have an SN2 reaction on an sp2 carbon. It needs to be an sp3 carbon, preferably methyl or propyl. Secondary as a least option. Okay? Now, another reaction, and we're not gonna look at the mechanism or anything, but ethers are notorious for reacting with atmospheric oxygen to form peroxides. And peroxides are extremely dangerous because, but a peroxide is something that has two oxygens next to each other, and these oxygens have no desire to be next to each other. Too many electrons to electronegative. This is a bond that tends to break homolytically to give you radicals. Peroxides are your typical radical initiator. And once you have radicals, then you go to radical chain reactions. And in this case, a radical chain reaction results in an explosion. So you have to be careful with ethers because you can have, a gallon jug of ether and it's sitting there, particularly if it's not well, the cap of the lid is not on tight, being exposed to oxygen and just sitting there, months sitting there, it is forming peroxides. So now if you go and try to use this, let's say you try to distill the ether to have a clean solvent. Well, now you're heating this thing to get it to distill, and the peroxides tend to be heavier than the ether, so the ether is, going to gas, condensing, collecting here, and on this end, what I'm heating is I'm concentrating peroxides. And eventually this is going to be hot enough and concentrated enough of peroxides to get a reaction, a chain reaction going and have an explosion. So you never let, if you're distilling ether, you never let it get anywhere close to dryness. That's really, really dangerous. You want to have lots of solvent in there. And always be careful with that heating. There's always a potential for it to blow up. One of my best friends was distilling a 5-gallon thing of ether, and it blew up. I think 20 years later, she was still getting glass out of her body. It was just horrendous.
What was she doing? What was she doing?
Oh, we were graduate students in a lab, so we
What
did,
did you learn about?
we work with chemicals in our lab, yeah, we do.
That's so dangerous. I would
There's all kinds of things that can be dangerous. That was, a bad accident, but that's something that's done in real labs. But you work, being a chemist is, you work with a lot of compounds that you need to be really careful with, either because they're carcinogens, because they are explosive, because whatever. There's a reason why we make you wear goggles in lab, because the potential for explosion is always there. So anyway, which makes it particularly idiotic not to wear now. Covering your eyes. So eyes are really, really important. Okay, so this was about alcohols, which would be an OH. The sort of sulfur equivalent of an alcohol would be a thiol, where thiol is an SH. Now, your sulfur is right below oxygen in the periodic table. Your sulfur has 6 valence electrons, it bonds like an oxygen to semicovalent bonds, but it is a lot larger, it is a lot more polarizable, it is a lot better nucleophile than an oxygen, right? Large polarizable that makes you a better nucleophile. So the properties are a little bit different. If you abstract this hydrogen, which is more acidic than the one in an oxygen. Why is it more acidic than in an alcohol? What makes something a stronger body, a stronger acid?
Conjugate bases.
The stability of the conjugate base. So if you put a negative charge here, that negative charge in a much larger sulfur is gonna be spreading the pain of that negative charge. That is a lot more stable. So more stable conjugate base means a stronger acid. So in terms of naming these things, this is a thiol. So rather than calling, for example, ethanol, if you had an OH, we call this ethane thiol. It is the thiol of, 2 carbons, something like that. So you name this like an alkane, add the word thiol at the end, and that would be this. If you're trying to name this as a substituent, what would you, if you were naming this as a substituent with an OH, how do you call an OH substituent? A hydroxy substituent, right? Well, this is a mercapto substituent. So this happens to be, this is called benzoic acid, this happens to be attached to carbon number 3 of the metacarbon of benzoic acid. We'll get to learn how to name these things, aryl halides and things a little bit later on in chapter 16 or so. But as a substituent, this is a mercapto substituent. So from an alcohol, this is an alcohol, it's a methanol. This is methane thiol. We said we can condense 2 alcohols together to form an ether. Well, we can condense 2 thiols together to form a sulfide. So this functional group, where you have a sulfur attached to carbon on either side, is called a sulfide. And you name it the same way that you name ethers, right? This would be dimethyl ether. This would be dimethyl sulfur. What's on either side? Followed by the word sulfide. Now, these 2, this is a condensation where we're losing H2S. There's another reaction that these 2 could do, which would involve losing hydrogen and connecting these 2 together. What type of reaction is that? When we lose hydrogen.
Oxidation.
Oxidation. This is not an oxidation, remember, gaining or losing water or H2S, which is an equivalent of water, it's neither an oxidation nor a reduction. This is clearly an oxidation. So your 2 thiols are oxidized to a disulfide. We have 2 sulfurs, so that's a disulfide, and this will be called dimethyl sulfide. Why is this an important reaction in biochemistry? Those of you in biochem. So there's certain amino acids, particularly cysteine, that have CH2SH sort of side chains. So if let's say here's a cysteine and this polypeptide chain, and here's another cysteine, this can be oxidized to a disulfide. And these disulfide bridges are very important to maintain the three-dimensional shape of a protein. Right? A protein, can start with a bunch of amino acids linked together, but eventually this thing is going to twist and turn and form this very, intricate three-dimensional structure. And one of the things that helps to maintain that shape are these disulfide linkages. So this is an important reaction in biochem.
I could use HBr to get that to right.
You could potentially have this pick up a hydrogen, but then the bromide will come in here and break this, you would end up with like methyl bromide and H2S or something like that. But if this came from HBr, then the bromide will come in and break this, and now you have methyl bromide and H2S. Is that what you're asking?
Oh no, sorry, I meant halogen, like Br2, I could do that. I could get the same product, but it says Br2.
Br2 can be an oxidizing agent. So under certain conditions,
That's not my halogenation, I meant to say Br2.
alright, so this would be a sulfide, or you can call it a thioether. Alright, so sulfur in the middle. In general, what you're gonna do is tell me what's attached on either side of the sulfur finishing with sulfide. So phenyl methyl sulfide or methyl phenyl sulfide. Or this would be like a substituent of this, which is called a thiobenzene. But by far the most common way of naming this would be what's on either side of the sulfur and then finish with sulfide. Now, thiols typically stick. All of your smells of skunk and garlic and whatever you can think of typically is coming from sulfur compounds, and particularly bad are thiols, although sulfides are not particularly good either. When you smell gas, you're not smelling gas. Methane gas doesn't smell, but they add to methane gas some methane thiol to make it smell, so that you know when you have a gas leak. Okay. The way to make thiols is via an SN2 reaction. Right, here's a salt, sodium, and this anion, and put it in the presence of an alkyl halide, preferably methyl primary, and then you just added this SH right here. Okay, that would get you a thiol, and then we can put a base, extract this hydrogen, have it attack another alkyl halide, and then you form a sulfide. Okay. Like I said, this is a stronger acid than an alcohol, so a base like sodium hydroxide is plenty strong enough. Form the thiolate ion, and then that thiolate ion is just going to attack an alkyl halide, which is secondary, and now you formed a sulfide. Alright. Of course, you couldn't do that in a tertiary. Alright. This is equivalent, this on the bottom is equivalent to which reaction? If we had an oxygen here, what would you call that? A Williamson ether synthesis. So that oxide ion, that's an alkyl halide, SN2 reaction, right? This is a Williamson ether synthesis, except rather than using an alkoxide ion, we're using a thiolate ion. But there's absolutely nothing different about it. It's the same Williamson ether synthesis. Okay. Okay, let's look at problem 5. So we're trying to make, ketone isopropyl sulfide, starting from butanol and to, you know what, I'm gonna get so tired of it. So butanol and propanol, and we're gonna form this sulfide. So show me, starting from the materials on the left, what reactions would you do? Let's say ultimately we want to do a Williamson ether synthesis, right? So it's a Williamson sulfide synthesis, whatever. Which bond would be best to make? This one or this one? The red one, right? I would want to come in with this thiolate ion attacking, let's say, this alkyl halide, because then we will be attacking a primary halide. So that means that somehow I want to convert this into this and then make the thiolate ion, and somehow I want to convert this into this, right? How do I convert a primary alcohol to a halide? How do I take one butanol to one bromobutane?
Oxidation.
No, oxidation will give me an aldehyde and a
Substitution.
acid.
SN2.
SN2 using PBr3, right? For primary, secondary alcohols, you convert them into halides by using PBr3, PCl3. What if this were tertiary alcohol? Then you use like HBr or HCl for a tertiary alcohol, because this is an SN2 reaction, so it won't work with PBr3 on a tertiary alcohol. So I but you use something like HCl or HBr. This is an SN2 reaction. Remember, this attacks the phosphorus, bromide ion leaves, then you have a good leaving group, so the bromide comes from the back and this whole thing leaves. Right, so this is an SN2 reaction. One of the reactions that we saw early on in the chapter. Keep these things in mind. Halides are very useful. You need to know ways of making halides. And we can make halides from alcohols. We can make halides from alkenes by adding HBr, bicarbonate or antimicarbonate, right? You should be building these things where you put something like this and you put, which are ways of building this, right? So this would be your antimicarbonate, so you would put some peroxides, if you wanted the bicarbonate with the bromide here, you would use it without the peroxide, and then, you know, look at, you could take this into a tosylate and make this, and then come in with like sodium bromide or something like that, and then that. You start building ways of making acid and building ways of making alcohols, and building ways you need to have this in front of you and keep reviewing it. If all we're gonna do is cover it once in the chapter, that's the one time you see it, this is not working. You need to summarize things like this and keep reviewing it and reviewing it. What are the ways that I know of making alcohol? What are the ways that I know of making alcohols? What are the ways that I know of making ethers? Okay, and just keep pounding at it and making exercises. Let's put this and let's put this. And now, you know, from here we can make all of these different things because this is a good leaving group and we can come in with a bunch of nucleophiles and displace it. So now you start the game of, oh, how do I make this from this? Well, through an alcohol. You know, you can make your own exercises. Start at one end, end up at the other, look at the steps in between. Okay, if you don't do that, you're gonna be dead doing synthesis. You need to practice doing synthesis. It's not a skill that comes to you naturally. You work at it and you work at it hard and sweat it until you start seeing the steps, right? But anyway, so see what I'm using. I looked at the product. I say, what is the key bond that I'm going to make? Okay, I decided to make this using Williams-Sonita synthesis except with sulfur. So now I'm looking at these are the two things I'm trying to synthesize to be able to carry the reaction that will make this bond. So now I need to start looking, well, these are my starting materials. How do I make this? So we saw how to make this right there. None of the thing on the bottom, just this one. How do I make this? Make this into a good leaving group. Let's say potassium chloride. And then add SH minus come and displace this. I could convert it into a halide as well. So come in with sodium thiolate ion, and that would give me this. And we just looked at that. We looked at ways of making thiols by coming with a thiolate ion and attacking something with a good BB. Right, so bromide, tosylate, one of those things. So now we have the two pieces that we need, let's put them together. What do I put first here? What do I need that is gonna attack this alkyl pair? We have thiolate ion. How do I make this thiolate ion? How do I get rid of this? With that space, right? A base like sodium hydroxide would be plenty enough. If this were an alcohol, I would need something stronger like sodium hydrate. But for a thiolate that is more acidic than an alcohol, sodium hydroxide is fine. That will form the thiolate ion, and then once the thiolate ion is formed, we add the halide, do the SN2 reaction, and this gives me my product. The first step forms this thiolate ion. And then this goes ahead and attacks this, and that gives you the product. We have, for practical purposes, finished with chapter 14. We could technically have the exam on Thursday. I am not going to, I'm going to give you a whole extra week to review this stuff. We're still only going to do the exam in chapters 10, 11, and 14. But obviously I'm going to need to get started with other material. But you have until Thursday next week to be reviewing this material, okay? Certainly go through class problems, print the blank ones from D12, practice on that, do the homework in the book, do your own problems. Start with this, let's do a couple of steps, okay, now let's build blank boxes and practice on that, okay? So starting on Thursday, we're going to start having the quizzes, okay? If you cannot make one of those 3 times, and again, that's, oh, well, we have a couple of other things. Oh, yeah, okay, never mind. We're going to finish on Thursday, but if you cannot make it to Thursday,
This Thursday.